Crystal graph neural networks have become important tools for predicting materials, properties directly from atomic structure. Their basic idea is simple and physically appealing. Atoms are treated as nodes, neighboring atoms define edges, and information is propagated through the crystal graph. But this raises a useful question. When we make a crystal graph neural network deeper, do we really need a new set of trainable convolutional parameters at every depth? Or can repeated application of the same learned local update recover most of the benefit of depth? A crystal structure is naturally represented as a graph. The set of atoms forms the node set, and the neighbor relations form the edge set. Each atom starts with a feature vector, for example describing elemental properties, and each bond carries an edge feature, usually obtained from interatomic distances. The first step in SR-CGCNN is to embed the raw atom features into a hidden representation. This gives each atom an initial learnable state, from which message passing can begin. At each message passing step, the representation of an atom is updated using information from its neighbors and from the bonds that connect them. The central atom feature, the neighboring atom feature, and the bond feature are concatenated. A gated nonlinear transformation converts this information into a message. The messages from all neighbors are then summed and used to update the atomic embedding. Repeating this operation allows information from progressively larger coordination environments to influence the final crystal representation. In the standard stacked SR-CGCNN, increasing the number of convolutional layers changes two things at the same time. First, it increases the message passing depth, so information can travel over a larger region of the crystal graph. Second, it increases the number of independent trainable transformations. These two effects are entangled. If a deeper SR-CGCNN performs better, it is not immediately clear whether the gain comes from the larger structural receptive field, from the larger number of parameters, or from both. The SR-CGCNN modification done here is minimal. The graph construction, atom features, edge features, pooling, and prediction head are kept unchanged. The difference is only in the convolutional part of the model. Instead of learning a different convolutional block at every layer, SR-CGCNN applies the same learned convolutional transformation repeatedly. This preserves message passing depth, but avoids introducing a new independent convolutional parameter set at each step. In spirit, this resembles an iterative refinement process. The same local rule is applied several times so that information propagates through larger neighborhoods. But it should be understood as a neural message passing architecture, not as a replacement for a specific electronic structure iteration. The direct three-step comparison makes the distinction clear. A standard three-layer SR-CGCNN applies three different convolutional transformations, with parameters θ1, θ2, and θ3. The shared recurrent model applies the same transformation three times. Both models therefore perform three message-passing operations, but they differ in how many independent convolutional transformations must be learned. This is the controlled comparison. Keep the propagation depth, but reduce the number of independent convolutional parameter sets. The result is not that SR-CGCNN3 beats the standard SR-CGCNN3 in absolute accuracy. The standard three-layer model remains slightly better. The important result is the accuracy parameter trade-off. For formation energy, the test mean absolute error changes from 0.0945 to 0.0986 electron volt per atom. For band gap, it changes from 0.4346 to 0.4503 electron volt. At the same time, the convolutional parameter count decreases from 66,432 to 22,912. In other words, SR-CGCNN3 uses only 34.5% of the convolutional parameters of SR-CGCNN3 while remaining close in predictive accuracy. The interpretation is that much of the useful effect of a deeper SR-CGCNN can be recovered by repeated local message passing, rather than by learning completely independent convolutional transformations at every layer. This does not make weight sharing universally optimal, and the five-step recurrent model suggests that more recurrence is not automatically better. But the three-step SR-CGCNN gives a compact and physically interpretable alternative to a standard stacked architecture. It separates the idea of propagation depth from the growth of independent convolutional parameters. That is the central point: depth through recurrence, not simply through parameter multiplication.